hello. Ooh. How's that? Better. So thank you for making it to the end of the day. You can come and claim your reward, a sticker, at the end if you want. So I'm Elliot West. I'm a principal engineer at the Expedia Group, and specifically I work for Hotels.com, which is owned by the Expedia Group. And today I'm joined by Jay, who was our intern last year, and she spent that year researching a lot of the topics we're going to be talking about today, and also building some of the tools that you're going to see. So I'll give you a bit of a backstory as to kind of how we got here and why we did all of this. Before I joined Expedia Group, I joined over 5 years ago. I worked for a company, and my kind of world looked like that picture on the left there. So we developed data processing jobs using technologies like MapReduce and cascading. And it was pretty magical, really, because we could define filters, functions, assemblies, and we could compose these into larger jobs. And as a Java developer, what was really nice is all of those small pieces, I could test them individually, and I could go home and I could sleep at night and I could feel really confident that the code I'd written was correct. So when I joined Expedia, my world changed, and it started to look like that picture on the right there. We had lots and lots of Hive SQL scripts, and they were used to produce critical data sets. They were very complex, and they were very large, and we didn't really have anything in the way of automated testing, so we relied much more on manual testing. And the problems with this were that whenever there was a feature added or a bug fix, it would take days and perhaps even weeks for that manual testing process to take place. And as you can imagine, they would find problems. And when they found problems, they would come back to us, we'd have to fix them, and then the whole cycle would begin again. And so we had these really, really long cycle times. So what a colleague and I really wanted to do was try and get back to that world on the left-hand side and decrease those cycle times. So the obvious thing to do was to hire a load of people who know Java and MapReduce, cascading, and then also retrain all the SQL developers as well to use this, and then we could rebuild everything. So we tried that. As you can imagine, it didn't actually work. It's really hard to hire people with those kind of skills. And also, while our SQL developers enjoyed having the opportunity to retrain and learn something new, ultimately, they were really frustrated because they'd gone from being sort of experts in SQL with maybe decades of experience to being beginners in these new languages. And so they weren't kind of feeling like they were being very effective. And even as a Java developer, I have to admit that if someone asked me to do some data processing and it had to be done quickly, I'd probably reach for SQL as well and start knocking up a SQL script. So what we kind of had to accept is we really do love Hive SQL. It's really powerful. It's really easy to learn. And if you've done any kind of computer science education or IT, you've probably been exposed to some SQL. And so that actually makes it a lot more prevalent and a lot easier to find people who can work with this stuff. But we still had those problems of that long cycle time. So instead, what we decided to do is see if we could bring that automated testing environment that we had with like Java-based languages and frameworks, and bring that to the world of Hive SQL. But before investing all of that effort in doing that, we kind of had to stop and think, is this really worthwhile? SQL's been around a very long time, over 45 years, and the world of data processing, the innovation is always sort of moving forward very quickly. Perhaps SQL's not going to be with us for very long. So I've got a timeline here, and then in 2005, you see Hadoop comes onto the scene. It kind of disrupts the world of data processing. We all start writing MapReduce jobs. And then over time, you get these sort of higher levels of abstraction with different frameworks. So things like cascading and Flink. And also you get, we're not just talking about batch processing anymore. We're also talking about processing streams as well, with things like Flink, Spark, and more recently even, Beam in 2016. But what I find really interesting about this is sooner or later, someone comes along on all of these frameworks and they will produce a SQL-based programming interface on top of it. So with Hadoop, it was Hive, but then you also see in Spark, it actually happened multiple times. And then even with that recent development of Apache Beam, there are efforts now to have a SQL programming interface there. Also, you see SQL appearing on those stream processing platforms as well, so things like KSQL. And now we do more data processing in the cloud. We use services to do that. And here too, you find that SQL is supported with things like BigQuery and Athena. So I think what this tells us is that SQL is going to be with us for probably a very long time, and that any efforts we take to improve the development experience around SQL is probably going to be a good investment. So our vision then as a team was that any data processing application we built, anything that was going to interpret, create, or alter data would have some form of automated testing, and specifically really unit testing. And we loved unit testing because it empowers developers. Developers can be writing their application code, and at the same time, they can write those tests, they can build that confidence that the code they're writing is correct, and they get this really fast feedback loop. They write some code, they run the tests, it's all green, hopefully, and they feel good about it. So that's really where we wanted to be at. And you can argue that writing unit tests takes a little bit more time, but what we actually found in practice is that finding these application issues early with hours worth of development on unit tests would save us, well, actually save the consumers of the data days spending clearing up that erroneous data that was generated by those issues. So what then were the challenges we found applying unit testing to Hive SQL? The first thing is that there isn't really a unit testing culture in the SQL community, it seems. Not many people do it. I think there's more reliance on manual testing. And consequently, the tools that are available weren't very numerous, and those that were available weren't that strong, not that easy to use. The second challenge we found is that SQL as a language, it kind of, I don't know, developers sort of tend towards putting as much as they can in as few scripts as possible. And so we ended up with these really large monolithic scripts. And unfortunately, unit testing is all about testing units, small units. And so these kind of scripts that we create aren't that amenable to that kind of testing. Here I've got an example of, this is 2 lines from a query of ours. I think it's it's over 1,000 lines long. And as a developer, if I sat down and looked at this and I had to, even if I was lucky enough to find that work out that the issue was in one of these 2 lines, it would take me a while to figure out what it was meant to be doing. And then if I then made a change to this, I don't think I'd feel very confident that I'd fix the problem, especially if I didn't have any tests to back me up. The final problem then is that even if we do write tests on SQL, we have no kind of feedback as to how good those tests are. What kind of coverage are we getting with our test suites? Maybe there's some high-risk business logic in our scripts that isn't covered. What percentage of the script is covered by our tests? And there don't really seem to be any tools that can help you achieve that with SQL. There are some great tools for languages like Java. So here's an example report from a tool called Codebases, and this is showing the code coverage of our tests for a particular class. And everything there that's green, the tool has identified that our tests run through that code. And that red line there is something it's figured out that actually the tests don't touch, so they never check that condition. So in this case, what that's kind of telling us is we need to go back and we need to write a test case that checks that exception is thrown under a particular condition. So it's a pretty useful tool. So the areas we wanted to focus on were identifying or building a unit testing framework. Unfortunately, we didn't have to build one in the end. We did find a good one. We wanted to come up with some patterns whereby we could break up those large queries into smaller components so we could actually unit test them. And then the final thing we wanted to do was come up with some kind of approach for generating code coverage metrics on our SQL scripts. And to do this, we ended up building a tool based on HiveRunner, which we call Mutant Swarm, which Joe will show you in a bit. So firstly, I'll just briefly talk about HiveRunner. So this is an open source tool. It was created and contributed by a company called Klarna. And what I really like about it is it allows you to both execute your Hive SQL scripts and run your tests just on your local machine. You don't need to have a test cluster or anything like that. So it's super simple. And it also means that you can have those tests execute as part of your build pipeline as well. So that's pretty neat. Your test cases with HiveRunner are defined using a mixture of Java and Hive SQL. And what that means really is that your SQL developers are going to have some kind of baseline knowledge of Java to actually construct those tests. However, HiveRunner is based on JUnit 4, which is a very popular unit testing framework in the Java world. So anyone with sort of Java knowledge should have some familiarity with it. So this is an example HiveRunner test. This is the magic at the top, really. This line here, this statement, it imbues the JUnit test with magical HiveRunner capabilities. So every HiveRunner test has to begin with this line. This next block, what that's doing is kind of setting up the environment for your test. So it's creating the kind of input tables to your process that you want to test, your script that you want to test. And you're also inserting your test data in that step as well. This block here tells HiveRunner where your script is that is under test. So this is a script that contains your data processing logic, your query that you've worked really hard on, and hopefully isn't hundreds or thousands of lines long. And then finally, these blocks here are the actual test cases. So these are methods, and you hopefully have more than one of these, unlike this example. And what you're really doing in these test cases is you're extracting data out of the result of executing your script, and then you're making some assertions on that data. So in this case, we're expecting that the script that we're testing is going to create and populate a table called db.etl, and we're just going to make an assertion. We expect there to be 42 rows of data in that table. So HiveRunner actually works just by first, for each test case, it's going to execute your setup SQL, then it's going to execute the script that's under test, and then over time it's going to collate together the results of executing those tests. So this is an example report there on the left, and that's saying there are 6 test cases, they all passed, they've all got green ticks. So that's nice. Okay, so that's the unit testing framework. The next piece then was, how do we break up these monolithic queries? So here's another example query of ours, and I've stripped out hundreds of lines here. But what I think you can probably see is there are actually 7 different queries in here. They're kind of nested in the outer query. And so it'd be really nice if we could extract all of these and test them in isolation, and then kind of compose them again and execute them as a whole. So we started to think about how we could do this. So we came up with a number of approaches that we'd like to try. The first we called chained tables, and this was actually a pattern that some of our engineering teams were already familiar with. They're already doing this. We thought as well we might be able to use Hive views to achieve this, and another option was perhaps using variable substitution for extracting queries and then sort of using variable replacement to put those queries back into place when we want to execute the whole thing. And then the final approach we considered was using HPL SQL. We wanted to just check whether that had any primitives for doing query composition, but unfortunately it didn't. So let's just look at those first 3 then. So here I've got a smaller sample query. And what we really want to do is separate that inner query from the outer query. So the way we do this in chain tables is you pull that out into a separate script file. And then what that script file needs to do is it needs to read in from the source table, but then importantly it needs to write its result out into another, call it a temporary table. So I've defined that as, I've called that table inner here. So that piece there, inner.sql, we can now test that in isolation. And then what we need to do on the outer query is, instead of executing that query in there, we can now select from the result that we stored in that temporary table. Another thing we have to do is we have to make sure that we execute that inner query before we execute the outer query. So there's a line at the top there, source inner.sql, and that's to include and execute the other script beforehand. So we end up with two queries. And for more complex examples, the pattern you see is kind of a sequence of queries being executed. They're all kind of reading in data from a source table, writing data out into a temporary table, and then ultimately at the end of the chain you get your kind of final result table. So what's really nice about this approach is it's, as I said before, it's kind of well understood by our teams at least. And another thing I like about it, it's got this side effect that if you want to debug the process, you can actually look into those intermediate tables and see what kind of values you have in there, so you can try and get an understanding about what's going on through your pipeline. However, we were worried that all this kind of reading and writing each time was going to create an unnecessary I/O, so they're potentially having a performance impact. Also, as these individual queries are executed in isolation in Hive, we're perhaps limiting the query planner, what optimization it could do, because it could only see each query individually, not the whole pipeline together. Okay, the next approach we looked at then was variable substitution, and here what we're doing is we're taking out that inner query. Again, we can test that in isolation, but this time in that outer query we're putting a parameter, a sort of variable placeholder. And so you end up with these two separate scripts. But what you have to do to then run your queries, you have to basically inject the SQL from the inner script into the outer script to build a new script which you're actually going to execute. So we wanted to use Hive vars for this, but it turned out that you could only really use that for sort of simple replacements like simple values. You couldn't actually use it for sort of SQL constructs to inject those into another query. So the next thing we tried was to use bash to do this, and once we did that, it did actually work. Sorry, what you end up with then is you have this process where you have your two separate script files, you have some process that brings those together to produce one larger script file, which becomes the thing you're actually going to execute as a query. So this isn't so nice in that it requires an additional assembly step, and if you're using bash to do this, then it doesn't feel that good that it's not pure SQL. So the final approach we looked at was using views, and in a very similar manner we take out that inner query, but this time we define it as a view, and that view can be tested independently. And now on that outer query we simply select from that view. So we end up with one query and one view defined. Now what's nice about this approach is Hive is actually doing the assembly for you, and as far as Hive is concerned, because it's doing the assembly, it sees one query, and so the query planner has potentially much more scope to optimize that. However, a problem we did find with this is that in reality a lot of those queries do have variables, parameters. Like it might be like if you've got a date range in there, you might define a start variable and an end variable. And you want to, each time you run a pipeline, you've got different values that you want to put in there. What we found with views is that those are only evaluated when you create the view. And so what this meant in practice is that every time you execute the pipeline, you have to drop and create the view, which, while perfectly feasible, just feels like, you've got to do this kind of extra kind of cleanup step. Another thing we kind of had with views is within our teams there was this belief that views were evil, and if you used views, that was just going to totally kill your performance. But there wasn't really kind of much rationality, really, I guess, behind that thinking. Perhaps it came from, I don't know, bad experiences with relational databases. So what we wanted to do then was understand what were the potential performance implications of using these different approaches. So at first we did this on a macro level. So with some example queries, we kind of decomposed them using the different approaches, and then using, we kind of looked at the query plan to understand how many different jobs were going to be created by the query planner and executed. And I think what you can see is that, as you probably might expect, the chain tables approach results in, a lot more kind of file moves and more jobs. But views is actually very similar to just having that one monolithic query. And I think, to me that makes sense, because what Hive is doing is pretty much, assembling all of that SQL into one query for you. The next thing we looked at was the execution time for these different approaches. So we ran lots of tests and average of results, and the key takeaways here is that all the approaches were actually fairly similar. And so I think what this meant is that our engineering teams are actually free to choose whichever approach they kind of felt was the best fit, so long as it wasn't writing the 1,000-line monolithic query. Also for us as well, it kind of demonstrated that views aren't evil, and there wasn't any real performance impact from choosing to use views. So we've documented these approaches and the kind of research we did into a blog post, which is linked there at the top. And also another good resource for unit testing Hive SQL is actually on the Hive wiki. So that goes on into details about the different tools available, different approaches, and also there's bits on modularizing queries as well. Okay, so we're at the point now where we've got our unit testing framework sorted. We've got some ideas on how we can break down those huge queries into smaller pieces that we can unit test. So now we wanted to start thinking about how we could generate code coverage reports on our Hive SQL. And so I'll hand you over to Jay, who will tell you what we did next.
Thank you. Am I on? Can you hear me? Oh, I can't hear me. That's really weird. Okay. So as Elliot mentioned, we're Java developers, so we're well aware that Java's got some really great testing tools which provide insights for code coverage, and also lets you know what isn't quite working with your code in terms of those red and green bars when you run your tests, letting you know that it's all passing or it's all failing, and also highlighting which lines are being covered and aren't being covered. And as a developer, this is really motivational, because as soon as you start adding more tests and making those tests better, those colors start to change and you see a lot more green. So that makes you want to write more tests to see more green. So we're also wondering if we can have this for SQL. So we looked into a couple of those existing Java tools, such as Codebases and PIT, and we found that PIT uses mutation testing. And we thought this could work for SQL, so we had a look into that. And if you don't know, mutation testing basically tests the effectiveness of your existing test suite. And it does this by taking your original program or query, and it's going to make some small changes to it. And these are referred to as mutants. And it's going to then take those mutants and run those against your test suite. And what you would expect is that if you're making changes to your original program, some of those tests in your test suite should start failing because that functionality has changed. So when you run those mutants against that test suite, if those tests fail, then that's a good thing, and that means that the mutant has been killed. However, if those tests still pass, despite the fact that your code has been changed, then these mutants are referred to as survived, and that's a bad thing. So the surviving mutants can sort of highlight where coverage is bad. and you can design new tests to kill those mutants. So the effectiveness of your test suite is then measured by the percentage of those mutants that are being killed. And we did some research into whether or not this could be done with SQL, and we found that there was a university in Spain which has an online web tool, which if you put your query into it, it will tell you different ways that query can be mutated. So that gave us the go-ahead to try and create a tool which actually performs mutation testing. So let me give you an example to help explain that a bit better. So we have some example test data there, which just has some hotels and their prices. And then we have a query in the middle, which is just going to select the lowercase version of that and their price, where the price is greater than 100, and it's going to order them. And then you have the result at the end, which is from running that query on that test data. And then right at the bottom, you have a test suite. This only has one test, but what it's doing is checking the outcome of that result. So it's checking the size of it, and it's checking that it's what you're expecting it to be. So those two hotel names. So then with mutation testing, what it's going to do is going to take that initial query, and it's going to identify certain things about it which can be changed. And we refer to this as sequencing. So these things that can be changed, we refer to those things as genes. And we group these genes into certain types. So for example, lower is a function, you can have columns and operators. And these types will have a set of mutations. So these are just the things that they can be changed to. So for example, if you have greater than, you can change it to less than, or equal to, not equal to, for example. So then, running that then, with that original query, it's going to create a number of copies of that query and inject a single mutation into those copies so that they then become mutants. So we've highlighted mutations there, and then these will all be run one by one against your test suite. And the X here means that the test has failed, which again is actually a good thing. And then in the top corner, you can see that one of those tests is still passing, despite the fact that the column of price has been changed to null. So what you can then do is then realize that this means that your coverage for that piece of code, so that column, isn't being covered. So then if you look in the test suite, you can actually see that it's not checking the price at all, it's just checking the names of the hotels. So then there's obviously a gap in your tests, so you can go into your tests and change them, add to them, write some more. But for whatever reason, sometimes you want price to be null. So if that is the case, then that just means that you need to add some more discriminating test data to cover that. So what we've done is built a tool called Mutant Swarm, which actually carries out this mutation testing for SQL. And we've built that on top of HiveRunner. And what it does is it allows HiveRunner to run through once and report back to you, letting you know that everything's working. And then Mutant Swarm will then take that original query and sequence those genes. Again, it just means it's going to identify all the things that it can mutate. And then it's going to generate all of those mutant SQL pieces. And then run each of those files against your existing test suite. And then at the end of all of those executions, it's going to show you a mutation report summarizing the results from that. And this is where it might get difficult. I'm just going to show you an example. Yeah, okay, so there's our lovely Mutant Swarm logo right at the top there. And you can see that there's this bar here, which is just letting you know the effectiveness of your test suite in terms of the percentage of mutants which have been killed. So obviously you want that to be as green as possible. And then you have some your original queries there, and certain things in the query have been highlighted. And ideally, we want everything in the query to be highlighted, because these are the things that are being mutated. But at the minute, these are the things that Mutant Swarm will cover. So if it's been highlighted green, it means that every single mutation for that gene has been killed. So again, that's a good thing. Otherwise, if it's red, it means that one or more of the mutations has survived. So if you click on it, it tells you what it's been mutated to and whether or not it was killed or whether it survived. And in the case where it survived, it's going to tell you which tests it survived in. So for example, test in a query, test out a query, and then you can go back into those tests to figure out why the coverage isn't good enough. And then The line number will just have a summary of how many genes are in that line, how many mutations, whether they were survived or were killed. And each time you run this, ideally you want there to be as much green as possible. So there are some minor challenges with this, just in terms of the execution performance, because HiveRunner isn't the fastest, and Mutant Swarm is built on top of HiveRunner, and this means then that the time for Mutant Swarm is proportional to the time for HiveRunner, multiplied by the number of genes you have for your query, multiplied by the number of mutations for all of those genes. So you can imagine that time's building up quite quickly. So it's not very fast. But we do have some potential solutions that we're thinking about. So for example, running those tests in parallel, or mutating only the changed sections of your query. So after the first time that you run Mutant Swarm, if you make any changes to your initial query, it's just going to create the mutations for that little change and not all of those mutations all over again. We could also take a look into HiveRunner and see if there's anything that we could improve with that, because then that would, we hope, help Mutant Swarm. Yes, so in summary, what we've done is built a tool which can help SQL developers to write more tests, but also to write tests of a better quality. And it can improve the quality of your data because it's identifying some bugs that you may not have been aware of. And we've shown you why it's good to do unit testing, and how modularization can help you with that, and also test coverage. And as I mentioned, there's stuff that we would like to work on in the future, so that execution performance, just making Mutant Swarm a bit quicker, but also increasing the amount of things that are mutated in that query. So as I mentioned, ideally mutating the entire query, if we can. So Mutant Swarm is actually open source on GitHub under the hotels.com page, if you want to take a look at that, have a play about with it. We've also got an email there if you want to find out about HiveRunner. And Elliot and myself are also on LinkedIn if you want to reach out. That's T-Bot and J Green with 4 E's, because 2 E's was taken. So yeah, thank you so much for coming. I know it's the end of the day, but I really appreciate it. Yeah, that's it.
Are there any questions? Could you use a mic, please?
Oh, yeah.
My problem with running and executing tests is always like the test data. How do you deal with that? So you always create like small mock tables, or you run it on actually copies of the production data? How do you deal with this kind?
Yeah, so I feel that pain. And I promise you that that pain is a lot less if you break your queries down into smaller pieces. So, you know, at the beginning, what we saw with those large scripts is, you know, engineers would write tests where, you know, they would assemble some test data for, I don't know, 600 columns, and, you know, then they would make some kind of, you know, assertion on all of those columns. But yeah, so by breaking it down and breaking those into those different test cases out, I think you can really kind of minimize the amount of test data you need to create, and you can be really targeted and specific. And HiveRunner as well has, you know, in that example I showed, there was this, you know, idea of running a test setup script, and that would have like a create table and then a lot of inserts in it. But HiveRunner does have this kind of builder pattern as well for building up test data, and that you know, takes a lot of the kind of boilerplate out of that as well. You can make assumptions about values of columns if they're not specified, so you don't necessarily have to provide every value for every row for every column. So yeah, I'd recommend looking at that. Could you use a mic, please? Sorry.
You explained that most of the skills of the team are about SQLs, and it's hard to move to Java for implementation. And the tests are written in Java, but even it's simple Java. And when you try to introduce tests, it's often hard to to fight with two facts. The first is the culture approach. SQL expertise doesn't have a huge culture of test, and the other one is the new language you need to learn.
Yes.
How do you deal with that?
You help people and you handhold and you give them examples to use. So I think with a lot of those test cases, much of it becomes boilerplate. You know, it's extract some data from the result and make some assertions. And so you just need to get those engineers up to the level where they're comfortable doing that. And yeah, often a good way of doing that is by copy and pasting and changing. But I agree, you know, that use of Java isn't ideal. It would be really nice to see something that is more familiar to SQL developers, a way of doing that. And that is something we'd love to look at, but you know, need time. Yep.
Yeah. Do we have time for another one? Yeah. Okay. Great. So yeah, I agree. It would be lovely to perhaps annotate the Hive SQL with actual expected values given this and this input data. That would be fantastic. By the way, fantastic work you did. Really appreciate.
Thanks for
HiveRunner. Well, yeah, you're perfectly welcome. So one question I have might be, apparently you cracked open the Hive query parser in order to get the parse tree and in order to generate these mutants, right? Mm-hmm. So that leads me to the follow-up question: what kind of other SQL engines would you be able to mutate in this fashion? Did you consider any others?
So yeah, I think your kind of assertion is a good one in that really all you need to be able to do is parse the SQL and understand the pieces of the SQL to use this approach. There's nothing really Hive specific about it. It's just the context that we've applied it to. So yeah, I believe you could do very similar with other SQL engines if you wanted to. But if you're offering to port it to some other system, that'd be fantastic. But we're big users of Hive SQL, so that's what we're targeting at the moment. Any more questions?
We have stickers.
Thank you very much.
The logo. Thank you, guys.